Hello friends, now we are going to discuss about the sign multiplication. In our previous video, we have discussed about the unsigned multiplication with the method of shift and add multiplier. Now we are going to discuss about sign multiplication. So here for the sign multiplication, we are using the Booth algorithm. This Booth algorithm for sign number multiplication is it will generate two n-bit product and treats both positive and negative numbers uniformly. So what we have to do, this algorithm suggests that we can reduce the number of operations required for multiplication by representing multiplier as a difference between two numbers. So we have to do the multiplication with the signed numbers. So we have, for that purpose, we have taken minus 7 into plus 3. So here the sign is represented. So the positive number we have taken as the multiplier as plus 3 and negative number we have taken as a multiplicand as minus 7. Before discussing with the Booth algorithm, we have to know the procedure. What are the procedures to be followed to perform the Booth algorithm? For that we have given the flow chart. So first we have taken 5 registers. That is A, it is accumulator register with it will store the resultant with the value of 0, and Q minus 1, it is also store the value of 0, and M is used to store the multiplicand, and Q is used to store the multiplier, and we have taken count, it is stored with the number of bits. It is stored with the number of bits. So now we have to perform the operation of the Booth algorithm for the sign numbers. So initial step, so what we have to do with the initial step? So we have taken minus 7 into plus 3. So minus 7, how to represent minus 7? Minus 7, if the negative number to be represented in the 2's complement method. 2's complement representation. If you take plus 7, if you take plus 7, if you take for example, if you take plus 7, plus 7, plus 7 will be represented as 0, 1, 1, 1. So 0 is represented whether the number is positive or negative. If it is 0, then it is a positive number. If it is 1, if it is a negative number. For example, minus 7 to be represented in the 2's complement of your number. So what is your 2's complement? We'll get 0, 0, 0. And we will add 1. So we will get 0, 0, 1. The sign bit will be represented as 1, 0, 0, 1. So minus 7 will be represented in the 2's complement as 1, 0, 0, 1. 1, 0, 0, 1. So this is your multiplicand. This is your multiplicand. Now what is plus 3? Plus 3 will be represented as plus 3. So how it will be represented? Plus, that is a positive number 0. So 3 will be represented as 0, 1, 1. So this is your multiplier. This is your multiplier. I think hope you are clear. So how to represent the negative numbers? The negative numbers will be represented in the 2's complement method. So in order to identify the 2's complement, what we have to do? We will take the binary equivalent of the number and we will identify 1's complement and add 1 into the resultant, then we will get 2's complement of your number, right? If it is 1, MSB bit is 1, it indicates the negative number. If MSB bit is 0, it indicates the positive number. Now we'll see step by step procedure. So we have taken count is equal to 4. Okay, so A register, it is initialized to 0, 0, and Q register will be stored with the multiplier. What is our multiplier? 0, 0, 1, 1, and Q minus 1 according to the initialization purpose, this is also equal to 0. And one more register we have used M. M is used to store the multiplicand value. What is our multiplicand? Is minus 7, that is 1, 0, 0, 1. This is your multiplicand. So we have done with the initialization process. We have done with the initialization process. Right? Now what we have to do after performing the initialization, we have to check with Q0 and Q minus 1. Q0 and Q minus 1. Which is Q0? That is LSB bit. Which is Q1 minus 1? That is MSB. That is and one more register that is represented as 0. If it is 1, 0. So what is the procedure here is we have to check with Q0 and Q minus 1. If it is both are 1 1 or 0 0, we have to perform the arithmetic shift right operation of a, q and q minus 1. So previously in shift add multiplier, we have taken only a and q registers. Here additionally we have taken one more register, that is called q minus 1. So here we have to perform the arithmetic shift right of a, q and minus 1. Right? So if it is 1 1 or 0 0, if q naught is 1 and q minus 1 is 0, that is 1 0, we have to perform a produces a minus m. If it is 0 1, you have to perform a produces a plus m. Then after performing this, we have to do again the arithmetic shift operation, and then we have to decrement the count, and then we will check the count. We will repeat the process. This is your process for the Booth algorithm. So after completing the initialization purpose, we are checking with q naught and q minus 1. What is q naught and q minus 1? That is 1 0. We have 1 0. If it is 1 0, what we have to do? We have to perform a produces a minus m. If it is a subtraction operation, we have to perform minus m. We have to take the multiplicand. We have to take the multiplicand, identify the 2's complement of the multiplicand and add with the result a. We have to identify the 2's complement of the multiplicand. What is our 2's complement of the multiplicand? What is our 2's complement of the multiplicand? Multiplicand 2's complement will be, again we have to check with the resultant. Multiplicand 2's complement will be, what is the 2's complement of the multiplicand? The sign bit remains, we have 2's complement, that is 0 1 1 0, again 1 is added, 0 1 1 1. This is your 2's complement of your multiplicand. 2's complement of your multiplicand. Okay, so our LSB bit is q naught is 1 and it is 0. So if it is 1 0, we have to perform a produces a minus m. So in order to perform the subtraction operation, we have taken the multiplicand and identifying the 2's complement of the multiplicand and added with the resultant a. What is a here? 0 0 0 0, and 2's complement is 0 1 1. So what we have to do? 0 1 1 1, and then it is remains same and 0. Here a produces a minus m. Performing the resultant, a produces a minus m. Then what we have to do after performing a produces a minus m, we have to do the arithmetic shift. What we have to do? We have to perform the arithmetic shift and decrementing the count equal to 1. When performing the arithmetic shift, right? So what you have to, this one will be here and this one will be here. All the other bits are shifted. So here we will get 0 0 1 1 and 1 0 0 1. This q naught bit will be shifted here. We are performing shift right and decrementing the count as 3. Okay, decrementing the count as 3, that is by minus 1. Okay, so now we have performed the arithmetic shift of a, q and q minus 1 register. Now checking with the count value, that is count is equal to 0. No, the count is 3. So again we have to repeat the process, checking with q naught and q minus 1. What is q naught and q minus 1 now? We have q naught and q minus 1 now is 1 1. If it is 1 1 or 0 0, just we have to perform the shift right. Only we have to perform shift right. So when we are performing shift right, we will get 0 0 0 1. This one will be shifted here 1 1 0 0. This one will be shifted here 1. We are getting shift right of a, q and q minus 1 with the count value decremented as 2. That is 3 is decremented as 1 as 2. We will get the resultant of 2. Now again checking with the count value. If it is equal to 0, then we have to stop the process. If it is not equal to 0, then we are repeating the same process. So what is the same process? We have to check with q naught and q minus 1. What is q naught and q minus 1? What is q naught and q minus 1? We have 0 and 1. If it is 0, 1, we have to perform A produces A plus M. Here it is represented A produces A plus M. So what is A? A we have, here we have 0, 0, 0, 1. M is 1, 0, 0, 1. 1, 0, 0, 1. When we are adding it, what will we getting the result? When we are adding it, we will get the resultant of, when we are adding it, we will get the resultant of 1001 is added with 001, that is 9. 1001 is equal to 9. We will get the resultant of 10. Just we are getting the result as 1010, and Q will be the remain same and Q0 will be remain same, and process here is A produces A plus M. A produces A plus M. After performing A produces A plus M, we have to perform shift right. We have to perform shift right. When we are performing shift right, what will be our resultant? What will be our resultant? We are getting 1. We are getting here, if it is a sign bit, the sign bit extension will be there 1 1 0, because this 1 bit is extended as the sign bit. So we will get 1 1 0 1 and 0 1 1 0, and here we have given 0. So it is shift right operation of A Q Q minus 1. When we are shifting the right operation, it is decremented, the count is decremented and 1. Again, if the count is decremented 1, if the checking with the count value, if it is not equal to 0, then we are repeating the same process, checking with the result that Q0 and Q minus 1, it is both are 0. Just we have to perform the shift right operation. So what is our shift right? This is sign bit. So sign bit extension will be like this. Okay. So similarly, when you are doing the sign bit extension, 111 0, this one will be coming here. This one will be 1011 and this 0 will be here. So arithmetic shift right of A, Q and Q minus 1. A, Q and Q minus 1. So count is decremented at 0. So when we are multiplying minus 7 into plus 3, we will get the resultant in the product as here. This is our product. This is our product. So 7 into 3, it is minus 21. 7 into 3 is minus 21. So how we will verify the result? We will check 21. Binary equivalent of 21. Okay. 1. We will get 2, 5, 0. 2, 2, 1. We will hit 2, 1, 0. So what will be the binary equivalent? 1, 0, 1, 0, 1 of 2. That is 21. That is binary equivalent is 1, 0, 1, 0, 2. 1, 0, 1, 0, 1, 2. So this is your plus, isn't it? So it is a positive number. So if it is a negative number, what I have to do? I have to take a 2's complement of this number. So take a 1's complement, 0, 1, 0, 1, 0, and we are adding the result. We will get 1, 1, 0, 1. Okay, 1, 1, 0, 1, and here it is 0. So what is the 2's complement of minus 21? Minus 21 will be represented as 1. So the equivalent binary number 0, 1, 0, 1, 1. So this is your minus 21 representation. What is the resultant we are getting? We are getting the 2n bits, isn't it? 2n bits. This sign bit is extended to 2n. How many bits we have? 1, 2, 3, 4, 5, 6. So the sign bit extension 8 bits, no? So we will get 1, 1, 1, 0, 1, 0, 1, 1. So by verifying the result of minus 21, we are getting the resultant in AQ register with the equivalent value. Thank you, friends.